Rahim. Assalamu alaikum. Welcome again to the continuous part for chapter 1, which is chapter 2, in particular part 1. So chapter 2 is quite long, so I'm planning to divide it into many videos. So let's first of all recall from the main result from chapter 1, which is the time-independent Schrodinger equation, which reads as follows. As we can notice in this equation, we have V. So V is not specified in the equation. So for each V, we'll have a specific solution for this Schrodinger equation. So the goal of chapter 2 is to discover for each potential, we'll treat specific potential, what's the shape of that wave function and what's the physical phenomena that maybe we can get from these kind of potentials. So this is the goal of chapter 2, which is to solve the Schrodinger equation for different potentials V. Now in this chapter and in this book, I believe, we'll just treat the potential to be just a function of position, because this is most of the physical phenomena happens. So for example, the electric potential is, for example, goes as 1 over R, where R here is X. We can treat it in one dimension as X. So most of the cases, the potential is just depends on the position, not the time. Now, the Schrodinger equation, as we can see, it's a partial differential equation because it contains a partial derivative. So we have psi, which is the wave function, which depends on X, the position and time, and we have a partial derivative for it. So this is basically the partial, what we mean by partial differential equation. Now, partial differential equations are in general a huge branch of mathematics, which we call it PDEs. It's just a short for partial differential equations. And there are many methods and many ways to solve it, and in general it's not easy. However, in this chapter and usually in physics, we restrict our weight or our method to solve it only in one method, which is very easy. And I would say this is the main goal of this video, is just to introduce you to this method because it's very important in a lot of physical application. طيب. So at the beginning, we'll introduce what's the method that we can solve this kind of PDEs. Then we will apply it to the Schrodinger equation, and we see how we can simplify the Schrodinger equation before we treat the different potential. So the method called the separation of variable method. And basically, if you have some partial differential equation can be written like this. Now this is just a random formula, or any random shape for the PDE. Could be any other shape, but as we can see, it should be linear. I will not discuss the details for it, so Allah يهينك, go and search what do we mean by a linear, but should be have specific shape such that we can apply the separation of variable. Okay, so this is just a random shape for it, and we have a function, a multi-valid function, so x and t depends on x and t, and we have, of course, the derivatives, the partial derivatives in x and the partial derivatives in t. Okay, now we started with this PDE. How to solve it? So this is the procedure. It's very easy. We have 3 procedures we need to follow, and boom, you will get the solution. So the first method, the first step is just to assume an ansatz. An ansatz just is a German word which means a form. So we assume a form, a شكل يعني شكل المعادلة or شكل للsolution. So we assume an ansatz, a form for the solution, which can be written as a product of a single valid functions. And that the name. ليش سميناها separation of variable? Because we are separating the variables into 2 functions. So this is our main function, اللي هو f, capital F of x and t. So originally it depends on x and t, but we assume that the solution can be written as a function purely of x and another function which is purely depends on t. Okay, so this is the first method. In other words, for now we are searching for a solution in this time. Okay, يعني حنا نبحث عن solution for the PDE, the partial differential equations, which can be written as of 2 functions, يعني one function of x and function of t. For example, يعني a solution could be يعني x square مثلا t cube. This is an example. Okay, so this is the first step, which is assuming the ansatz. Now after that, we take this form and we plug it back in our equation. Now notice, if we plug this form into this partial differential equations, these partial derivatives will become just ordinary or normal derivatives, okay? Because I have two p's, and each piece depends only either on only x or only on t. We will show an example and maybe it will clarify. So these are just the procedure. Now we plug the answers back to the equation, then do some more work and simplification. Eventually we will get, and I will show you that, we'll get two independent ordinary differential equation. So we reduce the one partial differential equations into two ordinary differential equation, ODEs. And in general, solving the ODEs is much easier than PDEs because we have a specific way how to solve that. Okay. Now this is the third step. After we solving these two independent ODEs, we get all the solution can be written in this form, right? Which is called the separable solution. But now we have a problem. You will say, okay, we found a solution, but we found a specific family of solutions, which is the separable solution. صح ولا لا? Because maybe I have a solution for the PDE, which can be written as, for example, x cubed plus t squared. But this form of solution, it clearly cannot be written as a function of t and a function of x. It's written as sum, not a product. So maybe you say, okay, we have a problem. We only found a very small set of solutions. I would say no. There is a fundamental theorem says that's the following: all the solutions, so any solution of the PDE, can eventually written as a linear combination of the separable solution. For example, اللي قبل شوي I believe I said x squared plus t cubed. It's a linear combination of a function which depends only on t and another function which depends only on x. Okay? So this is the main result why this method is actually working, because all the solution can be written as a linear combination of this special family. So for example, the general solution written like this. So the capital F, which is the function that we started with, can be written as one solution, one of the family of this solution, which is the separable solution. It's a linear combination, so we multiply it by a constant plus a constant, which is the second member of the family of that separable solution, etc. So in a compact way can be written as such. So this is the general solution for the PDE. Okay, so this is in a nutshell what is the what's the separation of variables method is. Okay, so it's very strong and used a lot. The most famous example is actually the heat equation. Again, search for it. Is an interesting example and it's easy to do it. Now, in other words, these members, which is the separable solution, are what's called a building blocks of any solution. So the procedure is to find these building blocks. After that, any solution is just a linear combination of these building blocks. In mathematical terms, and even in physics, we call these types of, or these functions, which is the separable solution, we call them a complete set of function. So basically a complete set of function, that a function, if any function can be written as a linear combination of them. So because any solution can be written eventually as a linear combination of g, for example, any function can be written as a linear combination of f of I, for example. We called f of I these functions complete sets, okay? Now, a useful fact before we go to an example to solve the PDE, or using the separation variable, is this fact. And it is intuitive, but I said let me just write it explicitly to be clear. So if you have an expression depends only on x, this is on one hand. On the other hand, so to equality, another expression depends only on t. This is for all t's and for all t and x. Then both expression must be equal to a constant. Okay, this is an example. So I have an expression that depends only on x, and I have another expression which depends only on t. Then according to this fact, both must equal to some constant. Now we can see that very clearly. So I have x plus x cubed is equals to t squared plus 1. Now let me change t. So let me put t is equals to, for example, 1. Then let me make t is equals to 2. So that will be 4 plus 1. And I will keep changing t, so the value of x also will be changed. So that means this expression depends also on t. But that is a contradiction, because we said that depends only on x. And similar argument if we take the opposite. So if we take, for example, t squared plus 1 is equal, so let me take again x equal to 1, so 1 plus 1, and t squared equals 2. Let me take 2 plus 8, and etc. So if we keep doing that, if we're changing x, the left hand side also will change. So it depends on x, but also that is a contradiction because it only depends on t. So therefore x plus x cubed equals to t squared plus t if and only if, if and only if it's equals to constant. Okay, so this I believe it's a clear but need an explanation. Now we go to a first example of finding the general solution. So this is just an example of the how we can use the separation of variable method to solve a PDE. So this is a typical PDE, and it's quite easy. So the first step is what? It is just write an answer, a form for the solution. So let me say that the solution can be written as a separation. So one function depends on x and another depends only on t. Now, so this is the first step. Step 2, which is the longest, is plug it back. So we plug g of t over the partial of t plus alpha. Maybe I need to change the color, but okay. X g of over, and that is equal to, and that is equal to 0. Now I can take, as we can see here, outside the derivative in this case, because the derivative, it is only on t, right? So I can take the function f of x outside, so that becomes a partial of gt over t plus alpha. The same argument I can take here g of t outside, because the derivative, it is on the x. So g of t partial f of x over partial x. Now there is a mistake I'm doing it here, and I'm doing it here intentionally to make sure that you understand the meaning for the separation of variable. So, which is writing the curly d. So we don't need here the curly here anymore, because this is a derivative on a single valid function, صح? So we have a single valid function and we're taking the derivative for it. So it's just a normal d, the one that you studied in calculus 1. So d. Now I need a page. Now we divide by f of x and g of t. So if we divide, let me just write it, f of x, g of t, f of x, g of t. I will have a cancellation here. So f of x will cancel with f of x, and g of t will cancel with g of t, and of course 0, we have 0 here over f of x and g of t, which becomes 0. So I will have d g of t over d of t over g of t plus alpha 1 over f of x and the derivative of f of x with respect to x equal to 0. Now we can just take f of x to the other side, equals to minus alpha f of x df of x. Now we can use the fact. How we can see it? On the left hand side I have an expression which depends only on t. So I have g of t and 1 over t. This all depends only on t. And on the right hand side I have also an expression which depends only on x. Of course alpha here is a constant. So using the fact, I will call just the fact, we will get that 1 over g, 1 over, I will just drop the t, dg over dt is equals to some constant, which is equal alpha minus alpha 1 over f df over dx. So as we can see, we have here two independent differential equation, ordinary differential equation. The first one, it is df over x 1 over f times minus alpha equal to c. So this is the first ODE. Let me call it ODE1. And the second, which is 1 over g dg over t, which is equals to c. So this is ODE number 2. Now we can solve them easily. So for the first one, ODE number 1, so what we will get df over f is equals to minus c over alpha dx, which means that if we take the integral for both sides, we'll get ln f is equals to minus c over alpha x, which means that f is equals to the exponential of minus c over alpha x. And similarly, in the same way, we get that g is equals to, I'll try to do it by looking, inshallah يطلع الحل صح. Yeah, e minus ct. So now this is the second step. What's the third step? So we get the solution that we want. So the third step is that the general solution, it is just the product of g, which is a minus ct minus c over alpha x, and to find the general for it, it is a summation of this kind of solution. So a summation of e minus ct minus c over alpha of x, and here the thing that we are doing the sum over it is c. So for different c, because this is a general solution for different c, times some constant alpha. Okay, so this is the general solution. Of course, c, I don't want to go to the details, but c could be a discrete or a continuous variable. So if it is discrete, for example, an integer, for example, c could be integer or a multiple of integer. So we take the sum over n, and if it is continuous, the summation will become an integral. Now, given this machinery, I believe now we are ready to apply it to that Schrodinger equation. So this is the Schrodinger equation, or the, if you want to call it, the time-dependent Schrodinger equation. So the first step is just to write it as a product of two functions. One function that totally depends on x, and the other totally depends on t, the time variable. Just let's forget about this, because after we complete the calculation, I will come back to this, to these two notation. Now this is the step 1. So let's go to step 2. Step 2 is just to plug the answers back to the Schrodinger. So we'll have I h bar partial over partial t. Let me write it in red. f of x g of t is equal to minus h bar square over 2m partial over partial x square, and we replace it with v of x g of t plus, maybe there is no space, plus here, let me write it, v of x and f of x g of t. Now allow me to drop the x and the t and know that f is a function of x and g is a function of t. So because I don't want to write every time f of x and f of t. Now as we can see, the same idea as the example. This is a derivative with respect to t, and this is a function of x, so it will not be affected, so that it will only affect the g. And similarly here, it's a derivative with respect to x, so it will only affect the function f. So if we organize it, we will take, from here, we will take f of x out. So we'll have f of x times IH. Now the partial derivative will become ordinary derivative because it is now applied on a single valid function, which is g equal to minus h bar over 2. So let me just erase this f of x and let me just write it f is equals to, we take again g of t outside, and it will be an ordinary derivative of f plus f or v, the potential v times g. Now again, we do the same as in the example. We divide by f of x, f o and g, sorry. And here we divide by f and g, and here we divide by f and g. This is, of course, is the derivative applied on g, and this is the second derivative applied on t. Okay. Now after simplification, so f will cancel with f, and here we have g will cancel with g, and f of g times, f times g will cancel with f times g. So the equation will be simplified to 1 over g. Let me take IH bar dg over t dt is equals to minus h bar square over 2m 1 over f, the second derivative of f with respect to x, plus the potential. Let me add a page because I believe we need it. Now we have two expressions. One expression depends totally on t, and the other depends totally on x. Again, using the fact, it's exactly like the example. And by the way, most of the separation of variable method using the fact, it is exactly like this procedure. Let me just recall something. As we can see here, is this right hand side is totally depends on x because the potential is only depends on x, and this the complication if we assume v is depends also on t. So if we have a potential that depends on x and t, the problem becomes a little bit harder. Okay. And that's why we first assume that, okay, the potential is only a function of x. So now we have two sides. One expression depends totally on t and the other depends on x. So we can say that I h bar over g dg over dt. So let me write g like this, is a constant. I will call it for now is e, and you will see why it's called e. So this is the first ordinary differential equation, and the second ordinary differential equation, it is minus over f d square f over dx plus v is equals to e. Now let's start with the first differential equation, which is this one. So if we just rewrite it, so it will become dg over g is equal to e over IH bar times dx, right? dt. Of course, I hope you know that 1 over I, it's equals to minus I. So this is can be written as minus I over h bar. Let me check it. Yeah, minus I over h bar e dt. Now we integrate both sides. We'll get in the left hand side, ln g is equals to minus I over h bar e t, which means that g of t is equals to some constant. Let us call it alpha, for example, exponential minus I over h e t. So this is the general solution for this, the first ODE. Now the second ODE, we can rewrite it, let me think. We can rewrite it as the following. So it becomes minus h bar square over 2m d square f over dx square. So I will just multiply by f plus f, the potential equals to f e. Now we cannot go further because the solution of this equation now depends on the choice of v. Okay, now this equation, I will do something. So it is the following. If actually it's usually denoted as psi of x only. So this equation is written as minus h bar square over 2m, the second derivative of psi of x over dx squared plus psi x v is equals to psi of x e. And this is called the time-independent Schrodinger equation. And this is the equation that most cases will use it in this course. Okay, so most of the topics that covered in this course, I believe even until chapter 12, will usually only solve the Schrodinger, the time-independent Schrodinger equation. Why is that? Basically because if you know that the solution of the time-independent Schrodinger equation, you will get immediately the full solution of the time-dependent, as we will see after a while. So now step 3. So let's assume that we know. Assume we know the solution of psi of x. So we have assume that we have psi of x. So the general solution, actually it is there. So the general solution, it will be just a summation of this psi of x times minus I h bar, over h bar t. So this is the general solution of psi of t. Now, especially that I want to just emphasize it is the following. Usually we denote the time-dependent wave function اللي هي تعتمد على x and t capital psi. So capital psi, it is for this. Okay, and the small psi, it is actually for the time-independent psi. So this one. So this is just in the box. طبعا في الكتابة it's difficult to distinguish between them for me, but I will try to write it as such. This is the capital one, and for the small one, this one. Let me try. Okay, and it will be clear from the context. Okay, so this is the separation of variable that we applied to the Schrodinger equation. So the general solution for the time-dependent Schrodinger equation will be something like this. So we have the wave function. It is written as these separable solutions. Okay, these called the stationary state, which is psi n's. So each one called the stationary state. Okay. Okay. So now we get the general solution of the time-independent Schrodinger equation, which can be written as a linear combination of each solution, of the separable solution. Now, usually I donate it by n, because as we'll see that in most of the example, this n will becomes integer, specific integer. So we'll have psi 1, psi 2, psi n, and for each psi we'll have, of course, a corresponding e. Where, of course, as we know, that psi n are the solution of the time-independent Schrodinger equation. Now this, mathematically, we said that it's called a linear combination, but in physics it's called the superposition principle, that any state can be a combination of two different states. And this is experimentally what the reason, the physical reason behind, for example, the interference pattern. So if we have an electron, as we discussed in the previous video, that sometimes you have an electron pass, so two electrons, but although they interfere. Why is that? Because the superposition between them. Now notice this that I just said that if we know the Schrodinger equation at time equal to 0, so we know it for any time. We just multiply by e to the power I minus in t over h bar. So that's why in most cases we just care about the time-independent Schrodinger equation, because if we know it, so if you know these, which is psi n's, so you will know, of course, the capital psi. Okay, so actually here's that the time is not an issue for us. Now this is an interesting example. It gives us psi at 0. So now, as I said, the difficult part is already given, which is psi 1 and psi 2. And it's asking for us to find this capital psi for at x and t, so the general solution for it in terms of alpha and beta. So we know, just write the solution, we know the following, that psi of x of t, the capital one, can be written as c1 psi 1, small psi 1 of x, e minus e1 t over h bar plus c2 psi 2 x e minus ie2 t over h bar. So what we need now, we need to find e1 and e2. But we know also that from the time-independent Schrodinger equation that minus h bar squared over 2m d psi, the second derivative, plus v psi is equals to e times psi. So for example, for e1, so we just put an index 1 here. But is it given this information? Yeah, this from here. So from here, what we need to rewrite it. So if we rewrite it, what we will get? So let me just copy paste it to see how we can play with it. So all what we need is just to rewrite it in that form, in this form. So we just multiply by minus, yeah. So minus h square over 2m dx. And if we multiply it and we take it to the other side, we'll have plus v psi 1, it is equals to minus h squared for 2m alpha psi 1. So now if we compare between this equation and this equation, we can see clearly that e1 is equals to minus h bar alpha over 2m. Now similarly, in the same way, because they have the same form, let me check. Yeah, they have the same form, as you can see. E2 is equal to minus h bar beta over 2m. Thus, the capital psi of t is equal to c1 psi 1 as a function of x, which is the small psi, minus, so in terms of alpha, So we'll have minus with minus will go, so we'll have I h bar, and that h bar تحت will cancel with the h bar square alpha over 2m t plus c2 2x. In a similar way, we'll have I h beta t over 2m. So this is the general solution in terms of alpha and beta. Now recall from classical mechanics that the total energy, which is in our case, it is equal to the Hamiltonian. It is just a sum of the kinetic energy and the potential energy. And the kinetic energy for a particle can be written as half mv square plus the potential. Now half mv square, we can multiply by m and divide by m, right? So if we multiply by m and divide by m, we'll have m square over m. So m square with v square, it becomes p square, the momentum square, which is equal just v, so if we square it, p square, and we'll divide it by m, so we'll have 2m plus v. Now if we want to change it to operators, because in quantum mechanics we deal usually with operator, so it's simply we just change the momentum to be a momentum operator, and the potential, it will be the same, because the potential is a function of x, and we know that the operator for x, it is x itself, so the potential will not be affected, it will be the same. Now what do we mean by a potential by the operator square? If we have a specific operator and I said square it, that means apply it to the function twice. For example, if I have the operator which is the differential operator, which basically you take the derivative for a function, which is d over dx. So if I said, okay, square it, that means apply it to the function twice, which means the second derivative. Okay, so this is the meaning of the operator square. So when we say the momentum operator square, that means if we have a function f, we just apply the momentum operator to it twice. So we can write it as p times pf. So we know that p can be written as minus, or the operator p is minus I h bar, the derivative of f. Now we take the derivative minus I h bar outside, and we apply this to it. So if we apply it, we'll get minus I h bar times the derivative again. So eventually it is clearly that we can get minus h bar square times the second, this applied to the second derivative of the function. So eventually the p squared, it is minus h squared, and the second derivative. So this is the momentum operator square. So it's very similar to the idea of applying the derivative operator twice. So we conclude that the Hamiltonian operator can be written in this form, minus h bar square over 2m, and the second derivative operator plus v. This is very important operator in quantum mechanics. It's the Hamiltonian operator. So that means that we can rewrite the time-dependent Schrodinger equation as follows. We know that the time-dependent Schrodinger equation is equal to this. So that is basically this basically is the Hamiltonian operator. So it can be written in this form. And this, by the way, it's a famous form of the Schrodinger equation. Now, in the same way, we can write the time-independent Schrodinger equation in this way. So as we can see the difference here, here we have a small psi, where here we have a capital psi. So for example, if we have a specific state, and we know that the state can be written as a linear combination of this. So we will have for each one of these psi n, they satisfy the Schrodinger independent Schrodinger equation. In other words, they satisfy this equation, and we will give it a name and the meaning, inshallah, in chapter 3 when we discuss. But in a rough word, the meaning of this, it is that the energy, which is En, it's an eigenvalue of the Hamiltonian operator. We'll discuss the specific meaning. But as we can see here, psi n for each n has an energy En. How about the capital psi, which is the linear combination of it is? of them. What's the energy for it? So we can deduce it from the constant Cn. So the Cn, if we square it, it's give us the probability of measure En. Because again, it's a linear combination for these. In other words, if, for example, psi of xt can be written as psi, let me say 2 of x e 1 t over h bar. So what's the probability of getting for this state energy E2? You would say it for sure it's 1 because it is in the state 2, right? Now, if it is a linear combination, let me call it here C1, C2, and for example C3, psi 3, E minus E2 t over h bar. Now, what's the probability of getting E2? It's not longer 2. It could be 2 or 3 because it's a linear combination again. So the probability it is C2 squared. So this is in a nutshell the meaning for it. So that's mean since Cn squared is a probability, so the sum for it should be 1, of course. Moreover, that the expectation value, which is the average, it's the probability of each energy times the energy, the quantity. Recall from chapter 1, which is if you have quantity J, so the expectation value for J, it is the probability of J over all the values of J. So the same thing here for the energy or the Hamiltonian H. Now let's take an easy example here. So we have a state which is given like this. It's a combination of psi 1 and psi 2. And he asks for A, what's the probability of measuring the energy to be E1, and what is the expectation value of the Hamiltonian. So for A, so what's the probability? So we need to find, in this case, what is C1? C1, it is A squared, right? But we know that A squared plus 1 over 2 squared must add up to be 1. So A squared is equal, of course I'm assuming that A is real, is equals to 1 minus half, which is half. So that is equals to, or that implies that A is equals to 1 over square root of 2. So what's the probability of getting E1? So the probability, let me call it P of E1, it is A squared, which is half or 50%. Okay, so there is a 50% to find it either in the energy either in E1 or E2. B, so the expectation value for H, it is, we can do, yeah, so it is A squared, or yeah, it's B of E J, let me write it like this, EJ, and the J goes from 1 to, and this is the general formatting for it. Now the probability of 1, it is 50% of E1 plus 50% of E2, so it is basically the definition of the average that we know, it's the sum over 2. Okay, it is only in this case because they are equally distributed, E1 and E2. So yeah, so this is the, in a nutshell, the introduction before we go to the introduction for chapter 2, before we go and we study more potentials. Inshallah, from the next video we will start the infinite square well, which is the first application for the Schrodinger equation and the wave mechanics, inshallah. Thank you for watching.